Hello friends. Now here I am going to start new chapter, that is shear stresses in beams. In the previous video we have seen stresses in beams, direct stresses, bending stresses already we completed. Now in this chapter we have some topics. It is distribution of shear stress across plane section used commonly for structural purposes and shear connectors. Here, first of all, I am going to explain you what is meant by shear stress. In the shear force and bending moment diagrams of a beam, we have studied that beam is subjected to both shear force and bending moments. In bending stress, we have considered that the beam is subjected to pure bending. Shear stresses in the beam are ignored. But in actual practice, shear stresses are also induced in the beam to resist shear force. It is necessary to know the shear stress distribution in beam and also find the value of maximum shear stress in order to check the beam in shear. In this chapter, the horizontal and vertical shear is only considered. You can see here, this is a vertical shear. You can see this diagram. Here you can see the applied force, this vertical shear. Here you can see the layers 1, 2, 3 is the horizontal shear. Shearing stresses in the beams. See, we know the Flexural Formula, that is M by I is equal to sigma by Y. Here you can see the neutral axis. Above the neutral axis you can see the forces at A, at point C. You can see from A to C uniform distributed load is given. The considered fiber, that is EF, is there. The distance from neutral axis, that is Y. See, this distance is dx. This is a cross section of beam. Entire depth is d. You can see here M, that is the bending moment at AB. And here you can see the M plus dm, that is the bending moment at CD. F is the shear force at AB. F plus df is the shear force at CD. Small portion of ABCD of a length dx of a beam with bending moment varying from M to M plus dm due to UDL or its length dx. Now you can see, consider elemental strip, that is EF, at a distance y from neutral axis. You can see here, this is the elemental strip. So we know that sigma is equal to bending stress across AB at a distance y from neutral axis. So sigma plus delta sigma is equal to bending stress across CD. I is the moment of inertia. We know the Flexural Formula, that is M by I is equal to sigma by Y. On face AB, sigma is equal to M by I into Y. On face CD, we know that sigma plus delta sigma is equal to M plus dm by upon I into Y. The force acting across AB, so force is equal to stress into area. So sigma into A is nothing but M by I into Y into A. Similarly, across CD, FCD is equal to sigma plus delta sigma into A is equal to M plus dm upon I into Y into A. Now net unbalanced force on the strip, that is FCD minus FAB. So delta F is equal to dm upon I into Y into dA. The total unbalanced force F above the neutral axis can be found by integrating from 0 to delta d2, d by 2. So here you can see here the limits are there. F is equal to integration of 0 to d by 2, dm upon I into Y into dA. So you can see this dm upon I into integration of 0 to d by 2 y into dA. But we know that integration of 0 to d by 2 into y into dA This is the first moment of area under the consideration from neutral axis, that is A into y bar. So F is equal to dm upon I into A into y bar. So we know that shear stress is equal to shear force upon shear area. So the formula is equal to F upon B into dx. Here you can see the diagram, that is dx, force into sheared area. Unbalanced force is balanced by shearing stress tau acting along the length dx and width is b. So formula, shear stress is equal to dm by I into A into y bar upon b into dx. So here you can see shear stress tau is equal to dm by dx into A into y bar upon b into I, but dm by dx is equal to s. Dm by dx is nothing but s. S is the shear force. So tau is equal to shear force at the section under the consideration, that is S into A into y bar upon bi. So this formula is very important. Tau is equal to S into A into y bar upon b into I. Here S is the shear force at the section under the consideration. A is the area above or below the layer under the consideration. Y bar is equal to distance of centroid of area under consideration from neutral axis. B is the width at the layer under the consideration, and I is the moment of inertia of the section. So please note down this formula for shear stress. Tau is equal to S into A into y bar upon B into I. B is the width at the layer under the consideration. I is the moment of inertia of the section. Here S is the shear force, A is the area above or below the layer under the consideration. See, different cross sections are there. Shear stress distribution over the rectangular section. Formula is tau is equal to SA into y bar upon B into I. See, this is the diagram for shear stress distribution diagram of rectangular section. You can see this diagram. For every section, you can see this is a triangular section. For triangular, this one is the shear stress distribution diagram. See, this one is the baseline. I have already given E content. So by using E content, you can make a chart for different laminas. Here you can see the shear stress distribution over a circular section. See this shear stress distribution diagram. Here in minimum time, I am completing shear stress distribution in I section also. You can see this is the I section. This one is the baseline. You can see this is the stress distribution diagram for I section. While solving the problem, you will get the more idea about this. This one formula is very important. Tau is equal to S into A into y bar upon bi. So average shear stress is nothing but tau average is equal to shear force upon area. See, this is very important. Shear stress distribution diagram for standard section. You can see this is the rectangle, circle, and triangle. You can see this. This is your shear stress distribution diagram for rectangle, circle, and triangle. You can see this. See, this is a T section and inverted L section. For that, shear stress distribution like will be like that. See, at this dotted line, you can see the maximum shear stress, that is tau max. You can see the symmetrical sections of hollow rectangle, C section, and I section. You can see this stress distribution diagram here. Tau 1, tau 2, tau max, tau 1 and tau 2 is given for symmetrical sections. You can see here unsymmetrical sections like C section. This is unsymmetrical I section. You can see the top flange and bottom flange dimensions are different. So shear stress distribution likewise, that is tau 1, tau 2, neutral axis. It is tau NA. This one is a tau 4 and tau 3. So different numericals are there. By using that numericals, you can solve the problem. University problems you can solve by using different formulas. Here we will take one important problem. One problem is, I think, sufficient to explain all the things. One university problem will give you the entire idea about the chapter. Very simple. Formula is there. By using previous concepts, you can solve this problem very well. See the problem. A beam AB supported at its distance has a span of 2 meters and carries a UDL of 200 kilonewton per meter over the entire span. The cross section of a beam is a T section having flange width 125 mm, flange thickness that is 25 mm, web thickness 25 mm, and overall depth is 200 mm. Calculate the maximum shear stress in the beam and draw shear stress distribution marking important values. The problem is from May 2009 for 10 marks. You have to read this problem very clearly, and then after that you have to write down the given data. It's a very simple problem. You can see the given data. Length is given, that is 2 meter. W is given, that is 200 kilonewton per meter. So first of all, draw the diagram. The wave dimension is given, that is 25. You can see the base 25. Entire depth, that is 200. You can see this one is vertical wave. Wave dimension is also given, and flange dimension is also given. It is 125. Base is 125 for flange, and depth is 25. So from this point to base, the distance is 175. So first of all, we have to find out the y bar. Y bar is the distance from baseline, distance from x-axis. So consider base as a x-axis. And now you know how to determine position of neutral axis. The first step is to calculate shear force is equal to support reaction. So formula is S is equal to W into L by 2. That is 200 into 2 by 2. That is 200 kilonewton is the shear force. Because the condition is given. Condition is given, that is span 2 meter. You can draw the diagram also, or you can take a direct formula. So UDL is 200. So 200 into 2, that will be 400 Newton, will act at centrally. So the beam is given, that is simply supported. So shear force is equal to 200 kilonewton. So next, that is position of neutral axis. So for that, you know how to calculate the area. So for area calculation, 25 into 175, that is A1 wave, and another one, that is flange. We have the dimension of 125 into 25. So after that, you will get the area 125 into 200 minus 25, that is 175. You will get answer 4,375 mm square. A2, that is 125 into 25, is equal to 3,125 mm square. Here we have dimensions y1 and y2. From bottom, how you know how to calculate the y1 and y2. Y1 is equal to 175 by 2. Y2 is equal to 175 plus 25 by 2. That is 187.5 mm. That is y2. Y1 is equal to 87.5. After getting the value of A1, y1, a2, y2, you can calculate y bar, that is a1 into y1 plus a2 into y2 upon summation of area. So the value of y bar is equal to 129.17 mm. So from bottom, the answer is 129.17. That is the distance from baseline, distance from horizontal x-axis. So y bar is here. You can see by this dotted line. So after that, the next step is to calculate moment of inertia. Here I am not wasting that much time to explain how to calculate Ix1 and Ix2 by using parallel axis theorem. You can calculate the value of moment of inertia about xx. So Ix is equal to Ix1 plus Ix2. Ix1 is nothing but Ig1 plus A1 H1 square. Ix2 is equal to Ig2 plus A2 H2 square. So here Ig1 is equal to BD cube by 12. Here Ig2 is equal to BD cube by 12. This is the dimension for first rectangle. These are the dimensions for second rectangle. Here, while calculating the distance h1, you have to take the difference between y bar and y of a particular rectangle. Here, while calculating h2, the distance that will be the difference between y bar and y of a second rectangle. So you will get the value of I, that is 29.56 into 10 raised to 6 mm raised to 4. Already n number of times we have calculated the value of moment of inertia. Similarly, you will get the moment of inertia. And after that, the main and important step is to calculate maximum shear stress at neutral axis. We know that tau is equal to S into A into y bar, y upon Bi. So here, the important topic is how to calculate maximum shear stress. Here you can see the area is equal to 129.175 into 25. See, while calculating maximum shear stress, you can take the area below the neutral axis. You can consider this area. So y bar into 25. Otherwise, you can take this area. See the cursor location. Area above the neutral axis or below the neutral axis. But you have to take a complete area above or below. Now here we are taking below. So area will be from this dotted line to this point, from this point to this. This is the rectangle, that is y bar into thickness, that is 25. So area will be 129.175 into 25. So area is 3229.25 mm square. Instead of taking this area, you can take top area also, means upper area also. You can see, first of all, you have to consider this rectangle plus this flange, area of this flange. You can consider that area also. But here we have taken area, bottom, you can see the lower area, and y is equal to, you know that you have to take y for particular area. So here, this one is the rectangle. First of all, you have to calculate the centroid point of that area. If you are taking this area, then you have to calculate centroid point of this area. But here we have taken this bottom area, so it's easy to find out the centroid. Centroid will be here, that is y bar by 2. So that y is 129.17 by 2, that is 64.59 mm. That is very important. You have to take y as a distance of centroid of that area, from centroid of that area to neutral axis, perpendicular distance between centroid and the neutral axis, that is y. So while calculating this y, you have to concentrate very properly. So the tau is equal to S, that is shear force that already we have, is the area that we have taken upper or below. Y is the distance, already I told you how to take y, upon B into I. What is by B? See, B is the width at that particular section. Here width is 25. So you can see width 25. into, already we have taken moment of inertia, that is I. By using this, you can calculate maximum shear stress at neutral axis, that is tau, 56.54 Newton per mm square. Then shear stress at a junction of a flange and wave. First one, B1 is equal to 125. You can see the flange dimension 125. And B2, you can see this dimension, that is 25. So B1 125 and B2 is 25. And area, that is very important. Flange area, that is 125 into 25. So area is 3135 mm square. And Y bar is equal, that is very, very important. Now here you are considering this top flange, only this top flange you are considering. So centroid point will be here. So that distance you have to calculate from neutral axis. So the distance is, you can see here at top is 125. So the distance from neutral axis to top, that is 200. This is the distance 200 minus the Y bar. You will get the distance from this point to this top, that is Y. So Y is equal to 200 minus 129.17. You will get extreme fiber distance minus 25 by 2, because centroid point of this area, centroid point of this flange will be here. So you can consider from this centroid point to this, that is the Y distance. So 200 minus 129.17 minus 25 by 2, that is 58.33. That is tau 1. Tau 1 is equal to S into A into Y upon B1 into I. So here we have the value of area, we have the value of Y. You will get the distance Y, B1, that is 125. You will get answer 9.87 Newton per mm square. Now the next, tau 2 is equal to tau 1 into B1 by B2. So here we have the value of B1 and we have the value of B2. So the answer will be 49.33 Newton per mm square. You can see here, again I am explaining you, while taking distance Y, you have to consider that area, complete area, and the centroid of that area, from centroid of that area to neutral axis. If you are considering this top flange area, then the centroid of this top flange will be here, and from that point to neutral axis, it is Y. So once you will get the value of tau 1, tau 2, tau max for T section, already I have shown you. For T section, you can see here, this is the baseline. For top flange, this will be the stress. As the area reduces, the stress will increase. You can see this. At a neutral axis, the stress will be higher, and after that, again it will comes to 0. You can see this is the stress, shear stress distribution diagram for T section. So n number of problems are there. You can see again T section, shear force. You know how to calculate shear force up from the section. So you can calculate this. Different sections are there, but the steps are same. First of all, you have to calculate Y bar. Then you have to decide. You can see Y bar, A1, A2, Y bar, moment of inertia. After getting moment of inertia, shear force, and then maximum shear force is equal to shear stress is equal to S into A into Y upon BI. You can see this is the I section. For I section, the condition is again same. Only you have to look focus on shear stress distribution diagram. See, this one is tau 1, tau 2, this is the neutral axis. Again, the conditions are same. While taking y, take y distance, take proper care. See the different symmetrical, unsymmetrical sections are there. Accordingly, you can find out the values. Already I have shown you the different laminas, different geometrical shapes and their shear stress distribution diagram. Maximum time in the exam they are asking T shape, I shape, L shape, C shape. You can find out the values for shear stress distribution diagram. See, one more important point in the chapter, that is a shear connector, that I will explain you in the next video. Here you can see this is the I section. For I section, you have to calculate y bar, then moment of inertia, then maximum shear stress, and after that tau 1, tau 2, tau 3. For top flange and for bottom flange, you have to calculate tau 1, tau 2, tau 3, and tau 4. And accordingly, you can draw this diagram. This one is tau 1, tau 3, tau 2, tau 3, tau 4. This is the neutral axis. By using our E content, you can solve n number of problems. Sometimes the problem will be the combination of stresses in beams. That is, by using different formulas, you have to find out. Same time, you have to draw bending stress distribution diagram as well as shear stress distribution diagram. I have completed both things, shear stress distribution also and bending stress distribution diagram also. So now you can find out shear stress distribution. You can draw shear stress distribution diagram. You can draw the bending stress distribution diagram. See, you can see here for T section, the bending stress distribution diagram is here, and this one is a shear stress distribution diagram. So keep in your mind, this is your cross section of a beam. This is the bending stress diagram, and this is the shear stress distribution diagram. Bending stress distribution diagram is different, and shear stress distribution diagram is different. See, you can see for the bending stress distribution, our required dimensions are YT and YC. In this shear stress distribution diagram, the formula is tau is equal to S into A into Y upon B into I. See, you can calculate the values by using formula. In the next lecture, we will see another topic. Thank you very much.